Okay, so this is a presentation on what a classical education approach to science might look like. So, what is a classical education approach to science? Well, in this presentation, I'm going to rely a lot on Pierre Duham's work. He was a theoretical physicist, did a lot of important work with producing equations for thermodynamics. He's also a historian of medieval science and a philosopher of science. Okay, so we got to lay some preliminary groundwork here. Okay, first of all, classical education as a medieval holdover, right? The foundation of medieval classical education was the trivium and the quadrivium. Now, the trivium was what we would today call qualitative, grammar, logic, and rhetoric. But grammar did not just mean language. It's also the meaning of the world itself. There was a grammar in the universe because it was created by the word of God, and there was meaning to it and intelligibility to it. The quadrivium was quantitative. And again, you had to learn these before you learned anything else. And the quadrivium was arithmetic, geometry, music, and astronomy. And if you want to think of it this way, it was arithmetic dealt with numbers, while geometry dealt with shapes. So music is numbers in motion, and astronomy is shapes in motion. So in a sense, you could see, though, how the quadrivium was really an extension of the grammar. We'll come back to this at the end. Now, we also need to make sure we're all up to speed on the language of deduction and induction. So imagine I give you a pile of words, pieces of paper with words on them, and you have to sort them into groups. Right? Now, that means you're going to have to figure out, by looking at these words, which ones go with each other. What are some common themes? Where do they fit together? That would be induction. Because you notice you'll be creating these categories in the process just by inferring them from what you see and all this evidence that's in front of you, this unsorted evidence. Okay, now imagine I give you that same pile of words, but I also give you headings. I give you the titles of groups, maybe vehicles, furniture, buildings, nouns for adjectives, and tell you to sort them into those groups. Now you're not coming up with the categories themselves. You're interpreting the data that you have in the light of pre-existing categories. That would be deduction. Deduction starts with premises and deduces conclusions from them. So for example, all dogs have ears, golden retrievers are dogs, therefore golden retrievers have ears. And then, are you taking these premises and interpreting the data you come across in light of it, let's say. Inductive reasoning starts with data, raw data, you could say, and infers general principles from them. So it could be all the golden retrievers I've ever seen have ears, therefore golden retrievers have ears. Or every time you eat peanuts, you start to cough. So inductively you reason, okay, well, you're probably allergic to peanuts. Or every cat you've ever observed purrs and meows. So therefore, that's what cats do. All cats are defined by the property of purring and meowing. So deduction is top down, inductive is bottom up, if you want to think of it that way. So first part of this presentation, we're going to talk about ancient science, medieval science, and modern science. Now, a lot of ancient science traces its origins back to Aristotle, who actually wrote the book on a lot of sciences, actually, but wrote the book on logic, the organon. The word organon, by the way, means instrument or tool. So he actually distinguishes between deductive and inductive reasoning in that logic textbook, right? And so science is actually based on deductive reasoning based on premises that are inductively arrived at. So let's give an example. Aristotle observes that heavy earthen material objects, when they're dropped here on Earth, they tend to fall downwards, right? And we notice that rocks that are made of earth, you could say, they keep falling out of the sky and landing on our planet, keep landing on Earth. So we can inductively conclude from that earthen matter tends to fall downwards. And they actually knew the Earth was round at this point, so you could say it falls towards the center of the Earth, because they know that if you dig a well or a hole or something and you drop, things will fall, down that hole. So the earthen matter tends falling towards the center of the Earth. And since there's stuff that's actually falling from outer space towards the center of the Earth, we can conclude this must actually be the center of the universe, and it's attracting kind of garbage from all over the cosmos. We inductively reason to the point of saying, okay, well, earthen matter falls towards the center of the Earth. Therefore, we deduce from that the Earth must be the center of the universe. It's the bottom of the universe, right? Where all the trash collapses into. Ptolemy develops his geocentric model of the universe by deducing from these premises. Now, what's interesting, and the idea was that the planets were revolving in these perfect spheres and concentric circles around the Earth. But the problem was that even at the time, even in these early days, before Christ, even, they were observing that some of the stellar movement and the planetary movement in the sky didn't seem to correspond perfectly to what the Ptolemaic model said they should be doing. So there was this proposed phenomena called epicycles. The idea of epicycles was that as the planet was revolving around the Earth, it was also kind of describing these little orbits as it went. Right? And that preserved the theory while modifying the account of the universe, right? You have the theory in place from Aristotle and Ptolemy. There's some evidence that seems to contradict it, so you come up with a sort of new account of the universe to explain how the theory can work and also to explain the phenomena you've observed. Okay? You modify the account of the universe. Then we get to medieval science, about which much could be said, but let's focus on two moments. One is the Summa Theologica of Thomas Aquinas, and the second is the Condemnations of 1277. Go over these both quickly. Now, Aquinas had studied under St. Albert the Great, who was quite a great physical scientist in his day. And Aquinas writes that in astrology, of course, back then astrology and astronomy were not sharply distinguished, the theory of epicycles is considered as established because thereby the sensible appearances of the heavenly movements can be explained. Okay, so we can explain what we see in the heavens using the theory of the epicycles. Not, however, as if this proof were sufficient, for as much as some other theory might explain them. So Aquinas recognizes the epicycles fit all the cosmological evidence, but he recognizes that another model might replace it, might explain it better, the phenomena better. So Aquinas is recognizing here that science does provide useful models. It provides instruments for predicting. We can use the epicycles and we'll accurately predict where we'll next see planets moving in the sky. But that doesn't mean that they perfectly describe reality. They don't necessarily describe how the universe is actually organized. They're just useful for predicting and observing the universe. Now, in 1277, the Bishop of Paris, the church in Paris, condemns several propositions of Aristotle as being heretical. They're incompatible with Catholic theology. One example is that Aristotle said that nature abhors a vacuum, so vacuums in nature are impossible. This is condemned. That limits God's omnipotence. God wants to create a vacuum, he can. Now, remember, Aristotle is the authority of science. So a lot of science is deduced from theoretical principles established by Aristotle. But now that Aristotle, a bunch of the stuff he said has been condemned, you don't have to follow him anymore. You're now freed up by theology to pursue all kinds of scientific lines of inquiry that Aristotle would have closed off. So Pierre Duhem says this was actually the birth of modern science. We often think of the church condemning scientists and restricting condemning what they're allowed to think as being a restriction on science, but Duhem says it's the opposite. By condemning these premises of Aristotle, they actually freed up science to explore new realms of inquiry. Now, speaking of modern science, it's thought to have begun with Francis Bacon and his New Organon. And notice that title, right? He's saying we got to move beyond Aristotle. Now, he proposes in here, and he didn't invent it, it predated him, but he articulates very well what we call the scientific method, right? Which is based on inductive reasoning. He's very critical and dismissive of the deductive reasoning. It's all about induction for Bacon. So you observe the world, you develop a hypothesis based on it, what you observe, using induction, then you test that hypothesis with an experiment, and you conclude from that experiment, that experience, you could also say whether or not your induction was correct. So that is the basis, in a lot of ways, of what was known as the scientific revolution that came out of this. Now, Copernicus, who was a canon at his local cathedral, he was probably a priest, noted that the patterns of the movements of the stars suggested that actually the Earth is revolving around the sun, not vice versa. So he writes a book about this called On the Revolutions of the Heavenly Spheres, which is dedicated to the Pope. Copernicus worked with the Pope on developing the new calendar, by the way, that we still use. Now, this caused some concern in some circles because it was thought that the Bible teaches the sun goes around the earth. A Lutheran theologian and astronomer named Osiander actually wrote an introduction anonymously to Copernicus's book, and in it he said, "This is a great. What Copernicus proposes in this book, the heliocentric model, is a great instrument for predicting where stars and planets are going to move in outer space." But that doesn't mean heliocentrism is true. It doesn't mean it actually is the real way that the universe is constituted. Now, Copernicus thought that yes, it was. But Osiander is saying, no, it's just a helpful instrument. It's a useful model for observation and prediction purposes. Now, this brings us to Galileo, who used the telescope, right? So now he's observing directly with this new instrument, this appropriated the spyglass, right, to study the stars. And he observed, among other things, that the planet Jupiter had 4 moons revolving around it. And that completely discredits the Ptolemaic model, right? It seems to, anyways, where everything is revolving around the Earth directly. Now, he put forward the telescope to prove this. He said, I found evidence that discredits that completely. But there were some natural scientists, like Cesare Cremonini, who refused to look through the telescope. In advance, they were like, I'm not going to look through it to see what evidence you claim you found, because I know it's fake. Here's what they maintained. They said, Aristotle's physics and Ptolemy's cosmology are so well established that if you think you found some evidence with your telescope that contradicts it, the problem isn't with them, it must be with your telescope. It must be a defective somehow. So notice that Cremonini is being deductive here. Given these premises, you found some evidence that doesn't seem to line up with it, must be something wrong with the evidence you found, or the way you found it. Galileo then, to explain, that what he'd observed, the moons around Jupiter and so forth, he espouses the Copernican heliocentric model, right? So the Earth is not stationary; it is revolving around the sun. And this was controversial for a lot of reasons. One is that it contradicted Aristotelian physics. Secondly, it contradicted a lot of scientific evidence at the time. And 3, it seemed to contradict the Bible. So, we've seen it contradicted Aristotle's physics. And Galileo did a lot of empirical studies that kind of contradicted prevailing physical notions, like on the Tower of Pisa, dropping a heavier object and a lighter object and saying that they actually fell at the same speed. The heavier object did not fall faster. But there was also a lot of physical science that did seem to contradict this. Just a couple examples. If we are revolving, right, you'd expect to see that the stars would kind of move in a certain way. All right, just like if you're on a merry-go-round, right, you come closer and then further away from the people you're looking at. That's called stellar parallax. We should observe that with the stars if we're rotating. But we don't. We don't seem to do that. The stars in the sky seem fixed in a way that doesn't seem to make sense if we are revolving. Also, if the Earth is revolving, then something that's kind of moving through the air in a straight line should kind of eventually curve, or it shouldn't land where it was aimed at. But again, that does not seem to happen. So you see, there were these legitimate scientific objections to Copernicanism. It also seemed to contradict scripture. There's a few verses that seem to say that the Earth is fixed and doesn't move. Now, St. Robert Bellarmine was the head of the Inquisition who tried Galileo's case, the first time anyways, and he wrote an interesting letter about the Galileo situation. Right? So he admitted that heliocentrism did explain the observed evidence pretty well. The term he used is that it saved the phenomenon. Better than epicycles did. Actually, he admitted, he said, this is a better model for explaining the phenomenon than epicycles are. So Galileo's heliocentrism is useful as an instrument of prediction and observation. But again, this is very similar to Osiander, right? If one wants to say heliocentrism describes the way that the universe really operates, that's problematic since it seems to contradict the Bible. But Bellarmine does say, he says, if you can really prove this, we're going to have to reinterpret some passages of the Bible. So he wasn't completely committed to rejecting it forever. But there's a very high standard here. You've got to really prove this before we are willing to look at scripture again and say we've been reading it wrong. So for Bellarmine, theological considerations were relevant to choosing which scientific model we wanted to endorse and embrace. And again, bear in mind, Tycho Brahe, who was a Lutheran scientist, he proposed a theory where all the other planets revolved around the sun, and then the sun revolved around the Earth. And you'll notice that explains all of the data that existed at the time, like the moons of Jupiter and everything. It saves the appearances. And it also avoids a bunch of the scientific and theological problems of heliocentrism. Uh, so you'll have this model in place. Why would you switch to Galileo's? Like, why would you go with Copernicanism? Then, of course, Newton came along and replaced Aristotle's physics with Newtonian physics. That's like Newton's three laws of motion, his law of universal gravitation, completely usurps Aristotelian physics and the four elements theories and all that. And it shows why and how planets revolved around each other much better than Aristotle's science had. So heliocentrism became generally accepted. Like Newton gave a good warrant to endorse heliocentrism. Then there was further scientific evidence that was discovered that explained away basically all the objections people had. So for example, things traveling through the air, they actually do curve their trajectories due to Earth's orbit. It's known as the Coriolis effect. And now with these advanced telescopes called heliometers, we actually can observe stellar parallax. So there you go. Here's the thing. Heliometers only observed stellar parallax in 1832. And the Coriolis effect was only proven in 1835. So heliocentrism, though, was accepted as being true well before this, right? It was the adopted scientific model, over 100 years before these were proven. So at a time where there was still glaring scientific problems with heliocentrism, it was still adopted as the major dominant prevailing scientific model in theory. Now, that being said, there were still things in the solar system that didn't seem to behave the way they should if Newton's physics are correct. For example, the orbit of Uranus wasn't exactly what it should have been, according to Newton's laws. So a scientist named Urbain Le Verrier noted that, according to Newtonian physics, that meant there had to be another planet that was out there somewhere, and the gravity was pulling on Uranus to kind of affect its orbit. Now, there was no observed physical evidence for this planet. It had never been seen in a telescope before. But despite that, Le Verrier predicted confidently there must be another planet out there. It's called Neptune, that's having that effect on Uranus. Notice this is not based on induction. This is not based on just extrapolating from the physical evidence. We've seen this planet a bunch of times, so it must be a planet called Neptune. It's purely deductive, right? Or at least it's deductive in the sense that it starts with a theory, it starts with Newtonian physics, looks at the data and interprets the data in light of this theory and says, given this, even though there's no physical evidence for it directly, there must be this planet out there called Neptune. So based on the theory, he modified his account of the universe to fit the evidence. He modified it to say there's a planet we don't know about yet, but it must be there. And it turns out Neptune does exist. That's pretty cool, right? But it's not that simple. Because Le Verrier noticed something similar in Mercury's orbits. They're also weird, so according to Newtonian physics. So he did the exact same thing for them. He said there must be a planet that we haven't seen yet that's affecting its orbit. He called it Vulcan. And there actually were reports. There were people who claimed that they'd seen evidence of Vulcan through their telescopes. So there's even some physical evidence for its existence, observed evidence, supposedly. But Vulcan, sadly, does not exist. So what actually is affecting Mercury's orbit? Well, to answer this question, we needed a whole new physical theory, and that is where quantum physics comes in. Quantum theory comes in. All right, just as Newtonian physics replaces Aristotelian physics, quantum physics replaces Newtonian physics or classical physics. It's funny because there's actually elements of quantum theory that are a lot closer to Aristotle than Newton, so it's like Aristotle's revenge. But the quantum physics theory of special relativity said that the mass of the sun was basically warping space-time, and that's what accounted for Mercury's weird orbit. Okay, so Newtonian physics had been helpful for observing and measuring most phenomena, like most things you're ever going to deal with in your life. Probably for most of us, the only stuff we're ever going to encounter in our lives meaningfully. You can use Newtonian physics and you'll be fine. When it comes to really large things or really small things, Newtonian physics does not work. So it's not the fundamental law of the universe. It's a very helpful instrument. It's a very helpful model, but fundamentally, it's not really completely true or real. Now, an interesting final point here. Now that we have quantum theory, neither heliocentrism nor geocentrism can actually be said to be more true than the other. And I try not to rely on too many lengthy quotes in this presentation, but this line from Stephen Hawking from his book, I think it's The Grand Design, it's worth looking at. It says, so which is real, the Ptolemaic or the Copernican system? Although it is not uncommon for people to say that Copernicus proved Ptolemy wrong, that is not true. One can use either picture as a model of the universe, for our observations of the heavens can be explained by assuming either the earth or the sun to be at rest. Despite its role in philosophical debates over the nature of our universe, the real advantage of the Copernican system is simply that the equations of motion are much simpler in the frame of reference in which the sun is at rest. So heliocentrism basically is just easier to use than geocentrism. It's a more helpful instrument, but it's not necessarily more true. And some would suggest that that indicates that maybe Osiander and Bellarmine were right. So having established all of that, what does all this mean for philosophy of science and for classical education? So we've seen that ancient science was largely deductive. Modern science, since Bacon and Galileo, has kind of claimed to be more inductive. But there's a big problem with this, which was identified by the philosopher David Hume, the famous problem of induction. So induction is based on all the examples of something you've ever seen before. So like, for example, every time we've heated water, that didn't have salt in it or something like that, to 100 degrees Celsius, it boils. So therefore we know that's a law. 100 degrees Celsius, water will boil. Every time we've observed a body acted upon by a force, the time rate of change of its momentum is equal to force. That's Newton's second law of thermodynamics. Every time we've ever observed that happening, that is held true, so we call it a law. It's the case with every scientific law. It's just every single time we've ever observed it happening, this law seems to have been operating, so we inductively infer that it's a law, and it'll always hold true, all based on previous experiments. But it could be that there are exceptions to these laws. We've just never seen them. A simple example, okay. It was once the case that Westerners had only ever basically seen white swans. So since we had seen this white swan, we saw this white swan, this white swan. Every swan we've ever seen is white. So inductively, okay, the definition of a swan is a white bird. But then they traveled the world. They went to, I think, Western Australia and observed, oh, there actually are black swans. So there you have it, right? This definition that goes back to ancient Rome of a swan as being a white bird, just overthrown, because now they found an exception to there. But that's the case with all laws based on induction, right? They're all just based on all the examples we've seen up till now. Maybe there are exceptions we haven't observed yet. So induction is not a strong enough basis for scientific knowledge. So Karl Popper says science can't be based on induction. Instead, it has to be deductionist. He says instead the criteria for science is falsifiability. So scientists will assert theories and then they conduct experiments to see if those theories are true or not. Or to put it differently, they test theories to see if they can prove that they're not true. That's really what it's about. Science can't ever say what's true. It can only say what's false. And if it's not proven false, it use it as until it is proven false, right? It's a scientific theory is one that not only explains all the observed evidence. It's not just something that saves the phenomena. It also has to, in principle, be falsifiable. You could falsify it. So for example, a scientist can say that all biological life depends on water. Okay, it's an assertion based on all the examples we've ever seen. All biological life we've ever seen has depended on water. So we can posit that. Now, can you ever prove that that's completely true? No, but you could falsify it. We could find an example of biological life that's not based on water, and that would disprove that theory. Until we falsify it, we just have to continue to work with it, right? So that's Popper's deductivism. Scientists can never actually confirm theories. They can only ever find evidence that corroborates them, or is consistent with them, or they falsify them. But Duhem, as well as a later philosopher named Quine, show that this does not work either. They argue that basically, for the most part anyways, an experiment can't falsify a theory. Duhem said this only applied to physics. Quine says it applies to all knowledge. I think the answer is actually somewhere in the middle. But still, it's a lot harder than Popper says it is. Let's look at an example of this. Okay. So if you do an experiment that seems to contradict a scientific theory, does that refute the theory? Or does it mean you need to modify your account of the universe and keep the theory? Or do you need to assume your experiment was somehow faulty? So, for example, did the fact that Uranus's orbit was weird, did that refute Newton's physics? Leverrier said no. It proved that there had to have been a planet we had no evidence of yet. We did not have to reject Newtonian physics. They weren't falsified. Instead, we had to modify our account of the universe. So the absence of any evidence for this planet was not proof the theory was wrong. It just meant we hadn't found that evidence yet. And in that case, he was right. Yeah. But Did the fact that Mercury's orbit was weird, did that refute Newton's physics? Leverrier said no, it proved there had to be a planet we had no evidence of yet. We didn't need to reject Newtonian physics, we just had to modify our account of the universe. The absence of any evidence for this planet was not proof the theory was wrong, it meant we just hadn't found that evidence yet. But in that case, he was wrong. There was no explanation for this within Newtonian physics. We had to switch to another theory to explain this. So in one case, the absence of evidence was a sign that we had to look for more evidence. In another, the absence of evidence was a sign that the theory was wrong. But how do we know which is which, right? How can we know when to modify our account of the universe based on an experiment or an observation? And when do we know when that experiment or observation has completely refuted a theory and we have to reject the theory altogether? This is a trickier question than it may seem at first glance, right? Because Popper tries to answer this. He says, well, sure, okay, we found Neptune, we didn't find Vulcan, but that's exactly it. When we couldn't find Vulcan, that proved Newtonian physics didn't work, and that basically falsified the theory. That does not work. Because if we didn't find Vulcan, you could always say that Vulcan is just made of some material we've never seen before. It's some kind of invisible and undetectable material. I mean, after all, isn't it easier to posit a new material we've never seen before than to say that the entire physical basis of modern science is wrong? Also, that's exactly what quantum theory does. Okay, it posits dark matter, dark energy, and dark radiation. And dark matter, according to quantum theory, it's not just one planet. It's supposedly, if it exists, it's most of the universe. It's like 85% of the universe. But it's never actually been observed. That's why it's dark, right? If there's no evidence for dark matter, or at least we've never observed dark matter, let's say, then why do scientists believe in it? Well, because, and there's other reasons for it, but it's basically from the effects that it supposedly has. They say there's some source of gravity is necessary to explain why galaxy clusters hold together. So where's that gravity coming from? They suggest that, well, there must be some undetectable dark matter, that there's lots and lots of it, and that's generating gravity that holds it together and explains this phenomena we can see. It's basically exactly what Leverrier did with the planet Vulcan. So there has to be some source of gravity that causes these effects that we can see. So I'm going to posit this thing there was no evidence of yet. Right. Also, what he did with Neptune, where he turned out to be correct, right? So to explain a phenomena, physicists can endlessly modify their account of the universe to try to save a theory. And Quine pointed out, or at least he argued, you could save any scientific theory by just adjusting your account of the universe. Like epicycles. Remember how epicycles were posited to save Ptolemaic system? So Quine famously said, any scientific theory, any claim really can survive come what may. No matter what evidence shows up, you can always try to save it if you just keep modifying your explanation of the events or the evidence. So when do you, let's just say Quine is wrong. In that case, when do you have enough evidence to decide you have to just abandon a theory and switch to another one? There's another problem here. It's closely related. All right, that's like the second law of thermodynamics. It says that a closed system will become disordered over time. Entropy will increase, basically. Now, what if you do a repeatable experiment that seems to show matter in a closed system with no additional energy entering it, spontaneously organizing itself? Well, there's two possibilities here, at least. One is that you have refuted the second law of thermodynamics. The other is that your experiment is wrong. You're missing something, or you did something wrong. And here's a quote from a scientist, Lord Arthur Eddington. It says, "The law of entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, well, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." So in other words, if you have an experiment or some evidence that contradicts the second law of thermodynamics, the problem is you did something wrong. You can never unseat the law of thermodynamics, second law of thermodynamics. And Eddington himself actually did an experiment in an eclipse to show that starlight bent in a way that confirmed Einstein's quantum theory. And a student asked Einstein, like, well, what would you have done if Edison's experiment had not gone the way you wanted it to? Like, what if his research actually contradicted your quantum theory? And Einstein's answer to this was, then I would have been sorry for the dear Lord, for the theory is correct. In other words, I would have been sorry for Eddington because he must have done something wrong. Because if his experiment had not agreed with my theory, I know my theory is right. So the problem would have been with him. He was so sure quantum theory was correct that he would have doubted any experiment that seemed to contradict it. He would have assumed the experiment was mistaken. But notice, Eddington and Einstein are both being very deductive here, interpreting the evidence in the light of this pre-existing theory and the categories that come with it. And also notice that is not all that different from Cremonini refusing to look through Galileo's telescope. They're just saying, well, if it seems to contradict Ptolemy and Aristotle, there must be something wrong with your telescope or how you're interpreting it. And in all these cases, the presumption is that the theory is so solid that any seeming falsifying experiment must be mistaken. Again, like Quine points out, a theory can be maintained come what may, really. So if a theory can't be falsified, then what determines which theory we actually go with? That's where Thomas Kuhn comes in. He has a very important book from the 60s called The Structure of Scientific Revolutions. And he argues that science works with paradigms. And that's what these theories are, right? A paradigm is like a big theory that explains a lot of evidence and its predictive power and all this. But it's a framework. I mean, the Ptolemaic model was a paradigm, and then Copernican heliocentrism is a paradigm, and Newton's physics are a paradigm, and quantum theory is a paradigm, right? And scientific communities work within paradigms. They adopt theories, which for a bunch of reasons, they adopt theories to work with and interpret the data in the light of these theories until they are persuaded, for whatever reason, and we'll maybe look at a couple of what those reasons might be, to shift into another paradigm. They end up deciding, maybe there's so much evidence that they decide, that contradicts this theory, that they say, okay, we can't really hold these both in abeyance. We're gonna have to abandon this theory and move to a new one. Or they just find a new theory that they like better, that they think does a better job of explaining the same phenomena, and move to that. That's called a paradigm shift. It has to do with the scientific community and what they choose to commit themselves to. Now, again, an example of this is heliocentrism. Like we've seen, when the scientific community adopted heliocentrism as its dominant paradigm, it was still riddled with problems. There were still lots of scientific problems with it that hadn't been solved yet. But they decided it's the best theory we have, and we're going to move on to it. And we expect that one day the science will end up vindicating it and solving these problems, right? Which happened largely. So it wasn't about this theory being proved by science. It was about the scientific community deciding that that paradigm did the best job saving the phenomena, and it was the most useful instrument to use. But of course, there's an obvious problem here, which is if you're a scientist, when do you decide to break with the scientific community and propose another paradigm? Because, of course, that is what Galileo and Copernicus did, right? They broke with the dominant Aristotelian and Ptolemaic paradigm, even though they didn't need to. The Tychonic system, as we've seen, explained all the evidence better and didn't have all the problems, or at least it explained them equally well and didn't have all the scientific problems. So what's a scientist to do? When do they know? When can they feel confident in abandoning the paradigm held by the scientific community and moving to another one? Again, let's go back to Duhem. Duhem says that a scientist needs to rely over and above just their physical observations and measurements on what he calls good sense, even common sense, he calls it sometimes. So if an experiment clashes with a theory, it's not obvious right away. Should the theory trump the experiment, or should the experiment trump the theory? Well, basically, the scientist for Duhem has to just rely on their good sense to make a judgment here about whether to doubt the theory, or doubt the experiment, or to modify their account of the universe. What does that look like? It can take different forms, and this is part of why scientific communities pick different paradigms, right? For example, many scientists think that beauty is actually a criteria for picking a scientific theory or model, right? Paul Dirac helped discover quantum mechanics, and he predicted the existence of antimatter. He once said it's more important to have beauty in one's equations than to have them fit experiment. Hermann Weyl was a colleague of Einstein at Princeton, and he said, my work always tries to unite the true with the beautiful. When I had to choose one or the other, I usually chose the beautiful. This goes to the point that there's this, as Wagner said, there's an unreliable efficiency, there's an unreliable effectiveness, as we called it, of mathematics in the physical sciences. For some reason, math is very, very good at, it clicks very well with physical science, even as predictive power in science, as we've seen with Neptune, right? Math even has predictive power in the physical sciences. And there's something beautiful about math and mathematical equations. So actually, if a theory is more beautiful than another theory, and they both explain the evidence, or in fact, even if one explains the evidence even better, but the other is more beautiful, less ugly, that is seen by some scientists as evidence that actually maybe it's more true or at least more useful. So aesthetic judgment is just as valuable as scientific judgment in some ways for them. There's also It also comes down to how you interpret your scientific evidence, right? So the Copenhagen School of Interpretation says that quantum theory, including the Heisenberg uncertainty principle, shows that reality itself is indeterminate, or there's an indeterminism, right? There's like an actual imprecision in the universe itself. I know Einstein, though, was sure that quantum theory it might be an accurate instrument for prediction, but it didn't capture ultimate reality. It might seem like there's uncertainty and indeterminism in the universe, but beneath that, in the actual reality of the universe, there was determinism, right? There was law, there was order, and there was logic. As he famously put it, this is a very interesting quote from Einstein: "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. God does not play dice. Right? The universe is not random like a dice roll, and indeterminate." But see, that's neither the Copenhagen School, Niels Bohr and all that, and Heisenberg, nor Einstein were relying strictly on the physical data. It's about how you interpret it, right? And you can see, so that means there's philosophical considerations that go into this, and even theological considerations, right? Like, does the inner voice, tell you, does the Catholic education you received? Because Einstein, he was not Catholic, but he had a Catholic education. Right. Does that tell you that this sounds true? So experiments and observations themselves are not sufficient to settle this. It comes down to how they're interpreted. So aesthetic, philosophical, even religious considerations are at play in which scientific models you choose. Right? So when Cardinal Bellarmine says that scripture is relevant to determining whether to adopt a scientific theory or not, maybe he wasn't being so unscientific after all. And so finally, like, Duhem was a Roman Catholic. He once said, "I believed it my duty as a scientist as well as my duty as a Christian to make myself the unceasing apostle of common sense, the only foundation of every scientific, philosophical, and religious certainty." Ultimately, you could say he defended neither sort of an ancient deductivist model or a modern inductivist approach, right? What he advocated was something close to the medieval approach to science. So he used deductivist models, but they can be revised or rejected in the light of inductive evidence based on good sense, which is informed by philosophy and theology, since science itself can't tell us when inductive evidence refutes a deductivist theory. Right? And that gives us some idea of what a classical education approach to science should look like. And it shows why the trivium, grammar and logic, came before the quadrivium. Right? If you want to look at it this way, scientific models are myths we study, not in the sense that they're necessarily like false, but in the sense that we recognize they are limited, but they point us to the truth by appealing to our reason and to our imagination. They're stories about how the world works that explicate the grammar of the universe, that we analyze logically, and that we assess aesthetically.